Let's continue in 1.6 and take a look at theorem 1.14 and some other things, of course. So theorem 1.14 is a property of the span of vectors. So this is called the subspace property of span. So you have vectors and you take the span of them, what happens? So let's take a look at that. Let's let W, the set W, equal the span, and this is how you can abbreviate SP, span of these vectors, W1, W2, etc., all the way to W sub k. So it's just arbitrary vectors in Rn. And we're going to suppose we have at least one vector in that span. K is greater than 0. And let's place those vectors for W sub i's being in Rn. And when you say something like that, it's just, we're not specifying which one. You don't really need to say I is between 1 and K. That gets a little too almost redundant. We're just saying that those vectors are vectors in Rn, which I forgot the vector symbol, didn't I? Let's try to put those in because we can't handwrite without it. Okay, so if that's the case, then W is a subspace. And we can show that somewhat easily. Then W is a subspace of Rn. May not seem obvious at first, but once we show the proof, that should give rationale to why. Basically, we need to show that any two vectors in W, when you add them, it is another vector in that span. And once we start looking at that, it should kind of make sense. So what we have then looks like this. So proof. Let's just adjusting my screen a little bit. Okay, so let U and V, and I'll try to be careful to make them look like U's and V's, be in W. So they are going to be linear combinations of W1 through WK. It could, remember, you have, it's an arbitrary R's as coefficients, so it could be kind of look like anything. Then let's write what those would look like. That form would look like this. Then U is going to equal R1, W1, etc., plus RK, WK, and different values of R, right? I mean, basically, if R1 is 1 and all the rest of those are 0, you get just W1. But it could be any linear combination of those vectors. And then V is different, or can be different. So V, we are going to say, is S1, and then we'll use S, right? And then plus, etc., W, S2, W2, etc., all the way to S sub K, W sub K. Where, and let's just say where they are, where the R sub i's and S sub i's are constants, arbitrary in R. Okay, so we're going to start there. Now, to show subspace, what do you need to do? You need to show that the sum is also in W and scalar multiple is also in W. So it's always those two steps of what we're showing. Okay, so let's take a look. Let's look at the sum. So U plus V is going to be all of that plus all of that. Right, so we have all of this, so write it out. I'm just going to do a little copying here just to kind of show you what I'm doing. It's that sum, and then we're going to add the other sum together, and then commute and simplify. So those sums are being added together. And then by commutative property and distributive properties, we can write it like this. Okay, so we'll say by commutative properties and distributive properties, don't need to get too detailed here, we have this equal to, so now we are essentially going to combine these together for W1. So we're going to take this, we're going to say, here's your W1, let's put those together, and then we're going to put together your W2s all the way to W sub k. Oops, I forgot a subscript there, didn't I? So when you do that, you factor out the coefficient, and you have R1 plus S1 times W1. And you do that all the way down, all the way to R sub k plus S sub k, W sub k. Now, isn't that, those are just real numbers here. So these are just real numbers because the sum of real numbers are real numbers, and that is in the span of W, or that is the span of that set. So that is in W since the R sub I plus S sub I is in R. It's arbitrary in R. So it would have been one of those R's, or I'm sorry, one of those scalar coefficients. Okay, so that's what we have. Now you just need to show scalar multiple, and it's of course very similar. Okay, so that was 1. And then 2, let's show that. Let's now let C be in R, and then we'll show the scalar multiple. So C times U is going to equal C times R1, W1 plus etc. all the way to C times R sub k, W sub k. And for same rationale, that is in W since CRI is in R. Okay, so this is also in W since C R sub I is also in R. All right, so because K is non-zero, meaning this is non-empty, because of that, it must be a subspace. So W is non-empty. All those elements, or the sum and the scalar multiple, place us back in W. Therefore, it's a subspace. Okay, so since K is greater than 1, meaning there's an element in there, W is non-empty. So W is a subspace of Rn. So we say W1 through WK, This will be a terminology we will use more later. So we say W1 to WK generate the subspace. So they generate W or the subspace W. So it's span. So in other words, W1 through WK, in this case by definition, span W. So the question sometimes comes up, what vectors do you need to span the set or generate the subspace? Okay, let's look at an example that puts some of this stuff in practice. So let's look at this example. All right, express the solution to AX equals 0 as a span of solutions. And then we're going to name that. That's actually called the null space or solution space. Okay, so let's just take a look at the example and we'll work it out. This one is already simplified. Yeah, this one's already reduced. So suppose you have this homogeneous system. System looks like this. And we have 1, 0, 1, 0, 0, 0, 1, 0, excuse me, -5, 0, and then the rest zeros, 0, 0, 0, 0, 0, and 0, 0, 0, 0, 0. Oh, you know what? Let's do this just because I can. I know it's a lot of work for dotted lines, but you know, it's trying to make it interesting. Okay, so you get this set. About as nice as I've ever made one look. Okay, so this is, we always like to label these, so let's go up here and say this is x1, x2, x3, and x4. Now notice that we only had, originally it would be only 2 equations like that. So add the rows to make up your basically 4 solutions. So basically what this means is you have 2 free variables. So when you have no pivots, essentially I'll try to use that terminology a little bit. Here's the first pivot, and then right adjacent to it a second pivot, and then no pivots. When you have no pivots, that tells you a number of free variables. But I like to put it in that form and kind of see what's going on. And then we solve this thing. We can see that x3 and 4 are arbitrary. They could be anything. We have some other stuff going on here. We could say simply, let's just keep in yellow, why not? x1 plus x3 is 0. So just x1 is negative x3. So we can do stuff like that really quickly. So x1 is negative x3. But x3 is going to be arbitrary, right? That'll be a free variable. Okay. Then we also have x2 minus 5x4 is equal to 0. So we'll be able to solve that. So x2 is negative 5x4. But then we have 0, x3 is 0, and 0x4 is equal to 0. So what does that mean? That means those are arbitrary. So we say x3 can be anything. We'll call it t. It doesn't matter the variables you pick. Usually it's RST, that kind of thing. x4, again, anything, is s. So that could be anything. And so they just want us to express that into the solution space. So because there's two free variables here, then we end up with two vectors in our solution space. And we'll do the span of it, call it that. So what we end up having then is this. Let's go back to our standard color there. Okay, so what we have is x3, or I'm sorry, x, our solution, is x1, x2, x3, x4. That's why we start to use subscripts, because you run out of letters. And then coming back to here, we have, in this we can say, and we can change colors to show you that we did it later. So here we can say this is basically negative, and then what was x3? That would be negative t. And then this one we can say, oh, look at that, looks cool, huh? This one we can say is negative 5, and then what's x4? That's s. So now you can put those in that form. And let's write it out like this. Let's say we have x1 will be negative t, x2 negative 5s, x3 is t, and x4 is s. So what we want to do is kind of break that up into a sum of two separate things. So like so you wouldn't be this, so you're put 0 in this place essentially. So we have these two, and then the other ones are different. Then you have these two. So you just do zeros in their place and then put the negative t and t. So you end up with, let's just do it one step at a time like this. Okay, so you have that, and then what's the other one going to be? And then we'll factor out the t in a second. Then this has, and then reverse it, 0, and then negative 5s, and then 0, and then s. And then you can see there that when you add these up, you get that, right? Add those, you get that. Add those, you get that. And add those, you get that. Now let's factor out the arbitrary constant. When you do that, you end up with negative 1, 0, 1, 0 times t, and then plus 0, negative 5, 0, 1 times s. So this is essentially a linear combination, right? So if these are arbitrary, then we can really just discuss the span of those two vectors as the solution, because the linear combination is implied or defined in the span. So when we say the span of this set, we get just the negative 1, 0, 1, 0. Hold on, I messed up my spacing there. Okay, so you end up with the span of this set. Make it a little bigger. There we go. of -1, 0, 1, 0, comma, and then 0, 5, 0, 1, 0, 5, 0, 1. And that's what they're referring to as a span of solutions. So this is called the solution space. For this system, but we really want to talk about the null space. So the null space is the span or the set of all vectors of the solutions. Now this is homogeneous, so the null space is referring to the set of all solutions of a homogeneous system. Or we'll talk about the homogeneous like counterpart to a system. So that's the null space, is the span of the solutions of a homogeneous system. Okay. Let's continue to the next thing. So this is defining, so that's the null space. We're going to define the row space and column space next. So here we go. So here's definition. We're going to let A be an in by M, does not have to be square in this case, matrix. And then we want to define row space. Okay, so we have row space and column space. So the row space is just the span of row vectors. It's rather easy concept actually. It's just a span of row vectors, and we'll talk about the meaning of which later, but that's what you have. And then the column space is, as you'd expect, the span of column vectors. So span of column vectors. And then as above, right, I'll just write that out again, the span of the solution vectors of AX equals 0 is a null space. So the span of solution vectors of AX equal to 0, right, homogeneous, is the null space, as we defined above. Okay, let's look at an example of this. And I went ahead and this time I just chose the book example because it's pretty just straightforward, but we can talk about it. So this is just from the book. So we have our matrix A, we're going to say is 1, 0, 3, and 0, 1, -1. Like that. So before we just start talking about span of vectors, null space, column space, and all that, let's just solve this, the homogeneous system. So let's just say you solve AX equal to 0 and see what you get. So what you should get will help us with the how to describe it. So when you do that, you put it into your matrix. Now, this might look not familiar, but can you go any further with this? I mean, you have a pivot here, you have a 1 here. Like, can you do anything else? Let's just put it in and see. So you have 1, 0, 3, 0, 0, 1, negative 1, 0. And then what I like to do is go, well, that's 3 of them, so we need 3 equations. Let's put in all zeros like that. So if you did that, and well, if you interpret this, there's no way to zero out anything else. So you really are in row echelon form. There's nothing else to do. You could just, if you have to, try it on your calculator, and you'll get exactly the same thing. So let's just suppose you did that. So let's do row reduced echelon form. If you did that again on a calculator, you get the same thing. Oops, I forgot to erase that. Okay, but the pivots are all there, really nothing else to do. Close enough. Okay, so this is already in row reduced echelon form. But putting in that row of vectors like this, I'm sorry, the zeros, putting in those zeros, I think kind of helps you say, oh, well, you got to have x3, right? So you have x1, x2, x3. So x3 is arbitrary. It could be anything because 0x equals 0. So let's come back over here and describe what those are going to be. So x3 is anything, which is in the reals. So x2, when you solve, you get just t as well, right? That's right over here. Oops, hitting the wrong buttons here. Okay, so that's this guy here. So you have just x2 equals negative t, add, and you just solve and you get just t. And then x1, when you solve for 3t, you get just negative 3t. So it's negative 3t. And so x is equal to, just like before, x1 is negative 3t, x2 is t, x3 is t. Now factor out the t. Sometimes you see it in front. I saw that earlier. I was going to put it in front. Sometimes you'll see t and then the vector. It doesn't matter. So it's negative 3, 1, 1. So that's our solution space. That's our null. So the span of that. So this basically is the span, right? It's a scalar multiple and there's just one vector. So the null space is the span of just that, which is basically what's sitting right here. But remember that a span is a set. It's a set. It's not just like a thing or solution. So now we can basically just list out the row space is the span of those vectors. The column space is the span of those vectors, and you don't put in the zeros now. You just put in what your original A was. So row space, column space, and then you have to calculate the null space. So therefore, what we have row space of A is the span of all of those. So you write down 1, 0, 3, and then 0, 1, negative 1. So it's 1, 0, 3, and then 0, 1, negative 1. And note that is a subset of R3, right? So it's a set. This is a set of vectors, scalar multiple, and you add them up of all of those, and it's a set. So and it has 3 elements in each vector, 3 components of each vector, and so that is a subset of R3. Okay, then we have the column space of A is the span of those column vectors. So you just put in the column vectors, 1, 0, 0, 1, and 3, negative 1. And that is a subset of what space? Is it R3, R4, R2, R? That's a subset of R2 because each vector has 2 components in it. So these are vectors in R2. It doesn't matter that they're column or row, it's just they're vectors in that set. And then we already figured out the null space. We just didn't write it like the null space. So the null space of A is the span of just that above. So it's negative 3, 1, 1. And that is also a subset of what? R1, 2, 3, 4. It's R3, again, because there are 3 components of the vector. All right, then we have what's called the, we'll talk about this next time. This is the column space, or give examples at least. This is the column space criterion. So the column space criterion is this, oops, let's try that again. What did it do that for? So a linear system has a solution if and only if B is in the column space of A. And it has to do with the span. We looked at that earlier about the span of the column space. So if B is in the span, then it works. So a linear system, AX equal to B, has a solution, could be infinite, but has a solution if and only if. Now this is non-homogeneous, right? This could be as any, a vector. If and only if B is an element of, right? So B is in the span of the column space. So the column space of A. So ponder that for a bit, why that works. And we have discussed it a little bit earlier, but this is kind of starting to piece all these things together. So we're going to use this stuff, and we start talking about like dimension and when you have solutions and infinite solutions and all that. Next, we'll do definition of basis for a subspace, standard basis, theorem 1.15, theorem 1.16, theorem 1.17, corollary 1.17, and theorem 1.18. So we've still got a bit to do in this section.